Good afternoon, my dear listeners. We continue our study of the theory of transmission lines with distributed parameters. In this lecture, we continue talking about the input impedance of a lossless line. We will talk about the short circuit at the end of the line. We will see how the magnitude and nature of this input impedance change and talk about how this can be used in practice. Before the lecture, I ask you to subscribe to our channel so as not to miss the release of new lectures. Put likes, it will help spread knowledge about our channel among the maximum number of listeners. Firstly, in tradition, let's remember what we discussed in the last lecture. In our last lecture, we learned that the input impedance of a transmission line in an open circuit condition is purely reactive and depends on the length of the line. We can control this impedance by changing of this length. The impedance is capacitive when the length of the line is less than quarter of the wavelength. With a future increase in the length of the line, its input impedance becomes inductive. And when the length of the line is exactly 1/4 of the wavelength, its input impedance becomes zero, meaning that such a line is equivalent to a short circuit section. These are the peculiar properties of transmission line with distributed parameters. But we can still learn more increasing information about transmission lines. And in this lecture, we will also discover many fascinating things. So, let's begin. This lecture, as you know, is devoted to a short circuit condition at the end of the line. Let's start by obtaining a mathematical expression for calculating the input impedance of a lossless transmission line in this short circuit condition. To do this, just like in the previous lecture, we will use the fundamental equations of a lossless transmission line, where the voltage and current at the end of the line are known. You recall that the fundamental equations are significantly simplified in the case of a lossless transmission line. Specifically, instead of hyperbolic functions with complex arguments, the equations now contain simple trigonometric functions of real arguments. We discussed this in lecture 13, which you can review at this link. In the case of a short circuit at the end of the line, its voltage, U2, is equal to 0. This allows for future simplification of the equations. The fundamental equations for a lossless transmission line in a short circuit mode are depicted as shown here. Please note that if we let gamma equal L, which is the length of the line, then these equations described the voltage and current at the beginning of the line. By dividing the voltage at the beginning of the line by the corresponding current, we can calculate the input impedance as shown in this formula. Pay attention to the fact that the complex input impedance of the line is purely imaginary. Do you see J letter at the front of the formula? This signifies that the input impedance of the line is reactive. Its magnitude and sign change with variations of the length according to the tangent law. We will learn how this impedance change in the following slide. This diagram illustrates the graph depicting the variation of the input impedance of the line with a change in the argument of the tangent, the product of beta and L, within the range from 0 to p radians. When the argument of the tangent is 0, the input impedance of such a line is also 0. As the length of the line increases, the input impedance becomes positive and increases, reaching an infinitely large positive value at half of p. This implies that the line is equivalent to an inductor with arbitrary, even infinitely large inductance within this range. With future lengthening of the line, the nature of the input impedance changes dramatically. It becomes negative, varying from negative infinitely to 0. In this range, from half p, as you can see, to p, the line is equivalent to a capacitor with arbitrary, even infinitely large capacitance. However, we discussed in the previous lecture, measuring the length of the line in radians is quite inconvenient. Therefore, in the previous lecture, we employed a different measure, namely the wavelength of electromagnetic energy in the line. The same graph using this new measure of length is presented on the next slide. In this graph, the length of the line is expressed in the terms of the wavelength of electromagnetic energy. The transition from the radian measure to wavelength was thoroughly explained in the previous lecture. Please review the previous lecture again if you do not recall how it was done. Looking at this graph, we can state that when the length of the line is exactly a quarter of the wavelength, its input impedance tends towards infinity, meaning such a line becomes an ideal insulator. Note that is an ideal insulator with infinitely high internal resistance. But at the beginning of our course, we mentioned that there are no electrical materials with ideal insulating properties. That's true, but a transmission line is not considered an electrical material. And we can harness this remarkable characteristic of the quarter wave line for our use. Let's envision a real transmission line through which electromagnetic energy is being transmitted. However, for such a line to exist, these conductors must be supported by insulators. So, in engineering, the same quarter wavelength line is employed to support for the conductors. As we have just learned, it functions as an ideal insulator. The thick copper wires of this quarter wave line are secured on a metallic base. This base is depicted here in the diagram. Contrary to our intuitive beliefs, these thick copper wires are ideal insulators. To be precise, for them to be ideal insulators, their length must be a quarter of the wavelength of electromagnetic energy in the line. Therefore, using this method to insulate power transmission lines, say at industrial frequency of 50 Hz, would be very challenging. In our very first lecture of this topic, here is the link to it. We established that the wavelength for a frequency of 50 Hz is 6,000 kilometers. Hence, to insulate a power transmission line, we would need to make metallic conductors that are about 1,500 kilometers long. You can see how impractical that is. However, for transmission lines in mobile communication, where frequencies are measured in gigahertz and the wavelength is about 17 centimeters, crafting insulation around 4 centimeters long is quite feasible. Thus, quarter wave insulator find application in devices operating at ultra-high frequencies, such as mobile connection and radar systems. So, and this lecture is over. In it we learned some interesting and unexpected things about the behavior of a lossless line when its output terminals are shorted. In particular, we learned that in the lossless line short-circuit mode, its input impedance depends on the length of the line. With an increase in the line length from 0 to quarter of wavelength, the impedance is inductive and can take on any, even an infinitely large value. When the line length becomes more than quarter of the wavelength, the nature of the resistance changes dramatically. It tends to be capacitive and can also take on any value. When the length of a line is exactly a quarter of a wavelength, the line has infinite resistance and is a perfect insulator. This fact is practically used in high-frequency technology for constructive fastening of the line. With this lecture, we have completed the study of lines with distributed parameters in a steady-state mode. But we still have a lot of interesting things ahead of us. In the next lectures, we will begin to study transient processes in line with distributed parameters. Thank you for your attention. Goodbye. Best wishes to all of you.